Hi, this is Jack Jackson with part 4 of our series of lectures on continuous distributions. This one is on using the TI-84 to examine these continuous distributions. It turns out that the TI-84 has a couple of built-in features that are very nice and very useful for helping us understand and actually compute values of probabilities, inverse probabilities, when we're dealing with CDFs and PDFs of continuous distributions. In particular, we're going to be looking at a situation where we know the formula for the PDF, and we'll be able to determine some things about the CDF and the probabilities. So let's start by reviewing here a minute. Remember, in a continuous distribution, that probabilities are areas between the graph of the PDF curve and the x-axis. So what this means is, remember that a PDF curve is always above the x-axis, and there'll be some area between it and the x-axis, at least for part of it. And when we take that entire area between the PDF and the x-axis, we get an area of 1. Okay, those are really the two conditions that makes it a legitimate probability density function. So if we want to find the probability that x is between a and b, what we want to do is find the area beneath the curve from a to b on x, and then of course below the curve on the top and on the bottom will be bounded by the x-axis. So we've got this line, vertical line at x equals a, x equals b. Those are the left and right sides of our region. The top is the PDF curve and the bottom is the x-axis, and that closes some region, and we want to find that area. Now, we've already looked at some triangular and rectangular distributions, and of course rectangles are very easy to find the area of, and triangles are pretty easy to find the area of as well. So in those cases we were actually able to use some formulas just from basic elementary geometry to find the area of a rectangle, base times height, and a triangular, 1/2 base times height. So we were able to do that. But what if we've got an area of a more complicated shape, some kind of irregular shape? How could we do that? That's what we're going to be learning about, one of the things at least that we're going to be learning about in this lecture, to use our calculator for that. So remember, the areas are integral notation, and it's for summing it up. Remember, we use a sigma for summing up. In the discrete case, we use this long skinny s. Instead of a Greek s, we use this long skinny s, which is called an integral sign, for summing up when we have a continuous distribution. So we're going to sum up all the probability density from a to b. So we get that. Now technically this is called an integral, a definite integral. Now if you've had calculus, or you're going to plan on studying calculus at some time, then you have or will study a lot more about this object right here. But we really don't have to know a lot of calculus. In fact, we don't have to know any calculus for doing what we're going to be doing in this course. All you need to know is this means sum up that probability density, that is, add up that area. So this is just another way, a notation that we're going to use for adding up that area, which is that probability when x is in that interval. So remember, s for sum. So let's take a look at an example. Here's something called an exponential distribution, and the PDF looks like this. It's some number lambda times e to the minus lambda x for x greater than 0, and for x is less than 0 it's just 0. So over here to the left of the y-axis we're just on the x-axis of 0, and to the right of that we have this decreasing exponential function. So basically we can ignore all this stuff where y is 0 all the time on the PDF. So basically we can just ignore this part where x is less than 0 and just graph and look at and compute with the parts where x is greater than or equal to 0. Lambda is a Greek letter, it's just a placeholder, a specific constant, but it's the same number here and here. So for example, this one down here I called it L instead of lambda. This one is 5 times e to the minus 5x. Now for this to be a legitimate PDF, this lambda must be a positive number. Okay? And again, we only need to consider the graph and the formula and everything for positive values of x's. Notice that the y-intercept 0 is 0 comma lambda. See, if you plug in 0 for x, minus lambda times 0 is 0, e to the 0 is 1 times lambda is lambda. So the PDF evaluated at 0 is lambda. So the lambda represents the y-intercept there. So it's going to start at lambda on the y-intercept and come down. So for example, our last one here started at 5 because lambda was 5, and then it comes down from there. So why don't you graph one using your graphing calculator where lambda is 0.5. Let's use y1 to put in the formula here. Replace the lambdas with 0.5 or 0.5, and then go ahead and get a graph. Now you're going to have to think about this a little bit in terms of what kind of window you're going to use. We know that x has got to be positive because this formula only applies for the positive. So we might as well start an x-min at 0. It's not completely clear how far to the right we need to go. We know that we don't need to go up above the lambda, so we could start the top at 0.5. It's usually a little bit better to go a little above that. And of course the y values start at 0 and go up. So you could let y-min be 0. I'm going to modify that just a little bit, you'll see here in a minute, but you could start with that. So please go ahead and do this now, please. Get your calculator out and do this. Press pause now. Okay, now you're back, and you should have already gotten a graph here. Let's take a look at what this would be. So we plug in our formula for y1, so we hit our y equals button, type in 0.5 e to the power, parentheses, negative 0.05 x, close parentheses. Remember, this is a negative, not a subtract. And to get e to a power, it's second ln key to get e to the power. Now, from 0 to 10 seemed a reasonable window for me to look at for x's. Actually, the x's in theory go out from 0 to infinity, but we can get a pretty good look at the graph if we just go out from 0 to 10. If I'm going to go out 0 to 10, if I put x scale as 1, then I'll get a mark every 1, which would be about 10 marks. That's pretty good. And y, I really need to start at 0 and go up to 0.5. I'm going to go just a little bit below that. I'm going to take negative 0.05 for the bottom, because I want a little bit of space here underneath the x-axis, and you'll see why in a little bit. But I want some space there, so I try to leave about 1/10 of the screen vertically here. So I take however tall I'm going to make the top, take about 1/10 of that and go down to the negatives, and leave yourself a little space at the bottom. You'll see why in a minute. So x scale is 1, y scale also 1. Actually, a y scale probably a 0.1 or 0.01 or something might have been a better choice. If you didn't use this window, go ahead and readjust yours to something similar to this. And then come back. Okay, by now we should have a graph here. And let's go on and see what we can do. So now we've got this graph. Suppose we want to compute the probability that x is between 1 and 2. So this amounts to computing some kind of irregular area. And we don't have any nice algebraic technique for that that's available to us. But fortunately, we have an area calculator built in the calculator. Okay? And it's called a numerical integral, or function integrate, FNINT. And so the FNINT is a numerical approximation of this integral, this sum of this continuous sum that we're talking about. And so basically the thing you need to remember out of all this is this, that this function integrate is a numerical version of this integral, but the main thing you need to know is that it is a area calculator. So the syntax is function integrate, and you put in your formula of your PDF. So it's function integrate, open parentheses. It'll open that automatically. And by the way, that's math 9. So math 9, it gives you the function integrate, open parentheses. Type in the formula for the PDF, which in this case is 0.5 e to the power, parentheses, negative 0.5x, close parentheses, comma. The second part is always x if you use an x here. It's telling you what the variable is. That's kind of what the dx, you can think of that up here as being just telling you what the variable is. So x is a variable, we put that there, comma. Now we give it our a and our b, that's our limits of our integral, that's the limits of where we're going, either side of our region we're finding the area of. So in other words, we want x's to go from 1 to 2. Okay, I've got an extra parentheses there, you only need one parentheses at the end of that. So, here's basically how we push the buttons to get that to happen. Okay? So, ultimately we're shooting for this last screen here. So you start by pressing Math, then number 9, and it's down here on the list, but it will be Function Integrate right there. So you can either down arrow to get to it and then hit Enter, or if you know it's 9, just press Math 9, it'll get it to come up. So that will get on the screen the Function Integrate open parentheses. Now we type in our formula, 0.5, second LM will give you e to the x, the negative key, 0.5x, parentheses, so close the parentheses on the power, comma, x, comma, 1, comma 2, close parentheses, enter. And so then you'll get this last screen and we get what we want. And so we know that area is 0.23865.12185, and that's the probability that x will be somewhere between 1 and 2, or about 24%. So we can do this at the home screen and work this out. We can also do this from the graphing screen and get an actual picture of the area too. And this is why I wanted to leave some space here at the bottom. So what we do is we go second trace, which is calc, and choose number 7, which is that integral sign. That's our S for sum. We're summing our function. Okay, and it's going to ask us for a lower limit. We're going to say 1, enter, upper limit, 2, enter, and then it's going to give us a shaded region and then compute the area of it. So it gives us a nice visual for the region we're shading, and it also tells us what the probability or the area of that region is, which in this case represents a probability. So in our context, this function integrate, what it does, or this version of it here, number 7, is a numerical integral. What that does is just calculates an area for us. And of course, in the PDF, the areas are probabilities. So it's basically summing up this area here. Summing up this probability density to get a probability of about 24%. So here's the page that sort of tells you all the steps. So from the home screen, our syntax, function integrate, it'll open parentheses, that's math 9. And then we type in the PDF formula, comma x, comma, then your A value, comma, your B value. Close parentheses. And then enter, and that will give you your area. This is your probability that x will fall somewhere between the A value and the B value. Next, we enter the PDF formula and y1 if we want to see a graph of it, and choose your appropriate graphing window. Sometimes that takes a little trial and error to figure that out, but we get an appropriate graphing window. Then we want to do second trace 7. Second trace is calc. Number 7 is the integral. Type in, it'll ask you for left bound. Type in whatever your A value is, and then enter. And then for right bound, type in whatever your B value is, enter. And the region will be shaded, and the area value will be displayed. Now let's try this out on something that we already know the answer to. Okay, something that we can do by hand. So just to make sure we've got a feel for it and we can kind of double check it as we go. So first of all, let's look at a uniform distribution. Let's look at uniform 1, 9. That is a uniform distribution that's defined between 1 and 9 and 0 outside of that interval. And first calculate this by hand, where we find the probability that x is between 3 and 7. And then after you've done it by hand, calculate the probability both just from the home screen and then also to calculate it and illustrate it on the graphing screen. Go ahead and do this and then come back. We'll check your answer here in a few minutes. Please press pause now. Well, hopefully you've done this. So from 3 to 7 is the part where we want to find the area, but the whole thing goes from 1 to 9. So from 1 to 9 is a width of 9 minus 1, or 8. And the height of the function then is the reciprocal of that, 1/8, so that when you multiply those two together, length times width, or base times height, you get an area of 1 for the full rectangle. And so when we graph this on the calculator, we're only going to graph it from 1 to 9. So we can just ignore anything outside of that because the probability distribution is 0. There's no probability density outside of this region, this interval from 1 to 9. Now, when we're finding the probability that x is between 3 and 7, we take just basically the base times the height. The height is a 1/8 all the way across, and the base is, in this case, 7 minus 3, or 4 wide, so we get 4/8 or 1/2 or 0.5, 50% is the area there, which is a probability. Now let's use the calculator to do it. Well, we can do it directly from the home screen. We can do function integrate, and our formula for our PDF is just a constant function, 1/8. Then you say comma x, comma, and we want to go to 3 to 7, so 3 comma 7, close parentheses, enter, and sure enough you get 1/2 or 0.5. Now, let's do it from a graphing standpoint. We graph the PDF, which is 1/8, y1 equals 1/8, and we need an appropriate window. In this case, the formula only makes sense from 1 to 9, so I'm only going to graph it from 1 to 9. If I go outside this, I'll still get the horizontal line, but the horizontal line really doesn't apply outside of 1 to 9. So I'm only going to just restrict my window to 1 to 9, and everything's good inside that window. Now, how far do I want the y's to go up? Well, they've got to go up at least 1/8, which is 0.125. I went up a little beyond that to 0.2. And if the top is 0.2, I need maybe a tenth of that, 0.02, down into the negatives. I went a little bit further, 0.05, down into the negatives. So I went from negative 0.05 to positive 0.2 for the y's. Graph that. Sure enough, I get a nice looking horizontal line there, and I can see the x-axis too. Then I do calc, which is second trace. To get calc, choose number 7. Ask me for lower limit, type in 3, enter, and upper limit 7, enter, and there it is, the last screen. It graphs that rectangle and says its area is 1/2. So there's a couple of different ways to get on the calculator. The first method, perhaps the shorter method, just types it in right at the home screen, and we get the area that we need. And you can take that area, that number there, and do other things with it if you want. The other way we can do it is on the graphing screen, but the graphing screen has the added advantage of you can visualize the shaded region there and where it is. Let's try another one. This time is another one that we can do by hand. This is a triangular region. So calculate by hand the probability that x is between 3 and 4, where x is distributed in a triangular distribution 1, 5, 1. Now remember the notation here. The 1 and the 5 are your A and the B, respectively. That means that it's only defined between x's from 1 to 5. So when I graph this later on, I'm going to just graph it from 1 to 5. Outside that, it's 0. So x min will be 1 and x max will be 5. And then the last number is the median. That's where the highest point occurs, and it's going to be all the way on the left side. I did it this way so that we don't have a piecewise defined function for the PDF. It's just a straight line, one single straight line, rather than two parts of two straight lines. Okay? So go ahead and figure this out by hand, and then go into your calculator and use your calculator to figure it out as well. And the two methods should agree, so you'll be able to check yourself. But then come back here, and we'll check it here as well. Be sure you do this yourself. This is really good practice. Press pause now. Okay, well you're back, and hopefully you're able to do it by hand here. Here's the by hand part first. So the base of the triangle is 5 minus 1, which is 4 units wide. The height of the triangle has to be 2 over that, so it's 2 over 4, which is 1/2. And let's just double check that. The area of the triangle, the full triangle, is 1/2 base times height. That's 1/2, 4 times 1/2. And that turns out to be 1, which is what it's supposed to be. The mode is at the far left end of the interval at x equals 1. So the formula of the PDF on that interval from 1 to 5 is simply the slope times x minus the x-intercept. Okay, this one starts at the high end on the left, and then it hits the axis on the right at 5. So the root or 0 or x-intercept is 5, 0. So you get x minus 5 there, and then you put the slope in the front. Well, let's see. The slope is y change over x change. It's dropping, so now it's negative, and it drops a half. So that's delta y is 1/2, now negative 1/2, and delta x, it goes to the right 4. So it's negative 1/2 divided by 4 is negative 1/8 is the slope. So the equation of the line is negative 1/8 times x minus 5. So the probability that x is between 3 and 4, we really want to think of this as a triangle, big triangle minus little triangle. The big triangle is going to go from let's see here. Okay, from 3 to 5, that's the big triangle. Bigger on the right, on the left at 3, going down to 0 on 5, so it's going all the way to the end. So that makes a triangle from 3 to 5. And then 4 to 5 is a smaller triangle. If we take that away, we get what's left over, which is the area of a, well, it's really actually a right trapezoid. But we can do it by a big triangle minus a little triangle. So the big triangle, of course, it's 1/2 base times height. Well, the base is 5 minus 3, which is 2. So it's 2 wide on the base. A half is because you always have a half in the formula for an area of a triangle. And then the height will be how tall it is at the, it's going to be highest on the left end, which is at 3. So we can use this formula, negative 1/8 times 3 minus 5. Let's see what we get there. 3 minus 5 is negative 2 times negative 1/8 is 1/4. So the big triangle is 1/2, the base is 2, and the height is 1/4. Now, the smaller triangle, we're going to subtract it off, so that's the subtraction. We still get a half. The base this time goes from 4 to 5, so that's a distance of 1. And the y distance, the height, is on the left side, which is negative 1/8 times 4 minus 5, so that's negative 1 times negative 1/8 is 1/8. So 1/8 is the height, 1's the base, and then we have 1/2 of that. So multiply all that together, we get the area of the big triangle is 1/4. The area of the smaller triangle we're taking off is 1/16. See, that's 4/16 minus 1/16 is 3/16 or 0.1875. Okay, it's kind of helpful if you actually draw it out too, but we're going to see that here in the next screen. Now let's do this with the calculator and draw it out. So we're going to use the calculator to graph it. So here we go. Function integrate, put the formula for the PDF. Well, on this interval, the formula is always negative 1/8 times x minus 5. Then you say comma x, comma, then a to b, 3 to 4, close parentheses, and you get 0.1875. We could have even changed that to a fraction, and it would have given us the same thing we got over there. Or it did give us the same thing we had in decimals. So if that's all we need, we could stop there. If we want to visualize it, then we're going to put our formula for our PDF, negative 1/8 in parentheses times x minus 5, for y1. Choose an appropriate window. Alright, well, we know the height is about a half on the left end, so I went up just a little bit past that, 0.55 above, and I went down negative 0.05. Maybe should have gone down a little bit further, but that's pretty close. To go a little bit below the x-axis for some space for our display down at the bottom. And we graph it, and it gets us a decent looking graph there. Now, then we do calculate, which is second trace, number 7. It'll ask us for lower limit, which is 3, enter, upper limit 4, enter. And it shades our area right there, which again is the shape of a right trapezoid. The way we did it by hand is we found the area of the triangle, the big triangle that went from the left edge here all the way down to this corner down here where it touches the x-axis. And then we took off this unshaded triangle at the end here to leave us the shaded region left over. There's other ways to do it, but this way graphs it on the calculator and it figures the area of this shaded region, which is what we want, which turns out to be 18.75%. How can we be sure that we have the correct formula? Well, one thing we might check is the total area has to be 1. So let's just check that. This rest of this is set up the same. There's the equation. There's the same window. Notice one thing I did is I cleared my drawing. So to clear your drawing, that's second stat, which is draw, and then it's the first one, number 1. So just hit 1 and enter. It'll say done, but then when you hit graph, it won't be shaded. If I didn't do this, I would have my shading left over from last time when I hit my graph. So you want to be sure you go ahead and clean off your drawing every time with the clear draw. Again, that is draw, which is second stat, and then you'll see it there. It'll be the first one. Okay, now we want to calculate number 7 again, and this time we want to go all the way from 1 to 5, which is the total region there, and sure enough, that area turns out to be 1. I'm sorry, I think I said something wrong. I said second stat. I should have said second program 1, enter. So second program gets you draw. So in general, when we have an exponential distribution, it has this form: PDF equals lambda times e to the minus lambda x for positive x's, or 0x, and for negative x's, the PDF is 0. So basically we can ignore it when x is 0, less than 0, and we only really need to consider this for positive x's. Now, the lambda has to be positive, and I claim that this is always going to turn out to be a legitimate PDF as long as we use the same value for lambda. But let's sort of verify that when lambda is 0.1. So there's 2 conditions we need to show. The first condition is that the y values of the PDF are always positive, or perhaps 0, but never negative. Okay? And when you raise e to a power, you always get a positive, and if lambda is positive, we multiply that by a positive, we're going to always get a positive output. So condition 1 is satisfied. Then the next condition is if we compute the entire area all the way from minus infinity to infinity on x, the total area between the curve and the x-axis, we get 0. So what we're doing is we're integrating from minus infinity to infinity the PDF dx, and it should be 1. So we're summing up that area. Well, in this case, we can clearly see there's no area we need to look at to the left of 0, in other words, no negatives. So we might as well, we know if we go from negative infinity to 0, that part's 0. So all we have to really check on is going from 0 to infinity, where this formula applies. We're letting lambda be 0.1, so we're finding this value here. Now, unfortunately, we can't put in infinity as a limit in the TI-84. If you've got a computer with a CAS computer algebra system, like the TI-89 or Voyage 200, or possibly the newer TI-Inspire CAS, then you can actually put in infinity in this, and it'll work out just fine. But we can't do that in the TI-84. So what we're going to have to do is we're going to have to pick a large number to approximate infinity. And on many of these distributions, they approach 0 so fast that we don't have to get that large a number to be reasonable for approximating infinity. So for example, if we put in 200 on this one, it'll be reasonably close for us because so much of the area is less than 200. In other words, if from 200 on out to the right, the graph is so close to the x-axis, that area that's under there is negligible for us in our practical sense here. So, here we go. We put in 0.1 e to the power negative 0.1x for y1. We graph it on a window from 0 to 200. See, I want about 10 marks, so I'll make them every 20. And we'll go up to 0.11 for y max and negative 0.01 for y min, and graph that, and that looks like a reasonable graph. And we want to calculate the integral then, or the area. That's calculate, second trace, 7. Lower limit 0, upper limit is 200, and it comes out to be 1 there. When I try this, or I could try this directly on the home screen. Function integrate, type in our formula, 0.1 e to the power negative 0.1x, close parentheses, comma x, comma 0, comma 200, close parentheses, and it comes out, well, just shy of 1 there. So maybe I should have gone just a little further than 200, and this would have come out to be exactly 1. Well, to the limits of the calculator. So here I decided to do it in the next one and use 300. If you look, don't look at the rest of it yet, just look at this first line. I just re-entered what I did and changed the 200 to 300, and now it comes out to be, well, as far as the calculator can go, 1. Now suppose we want to find the mean or expected value of this distribution. Again, this is the one where lambda is 0.1. Now the mean is the expected value of x. What you're doing is we're summing up x times the probabilities of x. Just like we did in the discrete case, except this time we need to use this function integrate thing to add them up. So all I do is take my previous thing that I had. I can just actually do second enter, and it'll come up with this formula here again. And then I go right back to the front of this where I typed in the PDF, right after the first parentheses, and just insert x times. And then hit enter, and it may take this a minute to figure out, well, a few seconds to figure out, but it does turn out to be 10. So 10 is the expected value, or the mean, of this distribution. What about the variance, or the standard deviation? Well, the variance is the expected value of x minus mu squared. So you first have to figure out what mu is, which we did, which is 10. And so where I had x in the last one here at the beginning, just the beginning part, I replace it by x minus 10 squared, and then do the same thing, and it turns out to be, well, it's actually 100. Okay, so approximately turns out to be 100. And then, of course, the square root of that is 10. So the standard deviation is 10, the variance is 100, the mean is 10. Isn't that cool? You can use the calculator to figure out this. And of course, this has some nice real-world applications, because we can tell how variable this distribution is, because it's both the variance and standard deviation tell us something about that. And we know where the center of the distribution is, the balance point. If we put that whole area, that irregularly shaped region, the balance point was to be the mean, which is also 10. Now another thing we can do is calculate the CDF. Well, we can at least graph an approximation of the CDF anyway. So we're going to graph this. So what we want to do is we want to put the formula of the PDF in Y1. And this screen shows you how to set up Y2. So you go down to Y2 and you say function integrate. Remember, that's math 9. And then put in Y1. Now remember, Y1 is variables, VARS, right arrow to Y variables, select, just enter for the function, and then enter again for Y1. Comma, X, always X after the second one there, comma, and say 0, comma, but instead of putting an upper limit of B, put in another variable X, close parentheses, and I said plus 0. Now plus 0 of course doesn't do anything, but in general what this plus 0 is, the 0 is the probability that X is less than 0. So whatever the probability of X being less than 0 is, replace it here. So suppose later on we do one, and let's say it's centered up, say the median is actually at 0, so half the area is below 0, then we replace this 0 with 0.5, because the probability that X is less than 0 would be 0.5. In this case, there is no area to the left of 0, so the probability that X is less than 0 is 0. And so we just have a 0 there. Now I say this because I want you to leave this Y2 set up like this for the rest of the course. You can just put your cursor on the equals here, hit enter to turn it on and off as needed. But then if you always put your PDF in Y1, then this will automatically give your CDF in Y2, and the only thing you have to change is this plus 0 at the end. You have to adjust that in the case that the area to the left of 0 is not 0. If it's some other number, put that number in. If you can do that, then you will get the right thing here. Now, I'm going to graph this from 0 to 100. And if we're going to do that, let's mark it off every 20 for the x's. And the y's are going to max out at 1. So I'm just going to put the top at 1, and we'll start at negative 0.1 for there. And so this will start at the origin, come up, and level out. So as with any CDF, excuse me, you're going to start at 0 and end up at 1. Technically speaking, this one actually has an asymptote there, but essentially it's at 1, or at least approaches 1. Well, what good does it do us to have a CDF? Well, there's several things you can do to CDF. So, for example, we can say, what if we want to find the probability that x is less than 10? Well, that's the y values on the CDFs are the probabilities that x is less than that number or less than or equal to that number. So if we want to find the probability that's x is less than 10, we just do a trace. So hit trace, type in 10 and enter, and it'll take you to the point on the graph where x is 10 and tell you what y is. Or we can look at the table and make sure we've got 10 in the table and see what the y is that goes with that. Either way, we get about, well, looks like about 63.2% of the area is to the left of x equals 10 on the PDF curve, and on the CDF curve the y value is 0.63 when x is 10. In either case, that means that the probability that x is less than 10 is 0.63. So notice that this means in this case that remember 10 was the mean, and so the mean is actually to the right of the median, because the median is going to be when the probability is only a half, and the probability, cumulative probability is a half. And here the cumulative probability is about 63%, so that's a little bit bigger than the median. Now, what if we want to find the probability that x is between 3 and 10? Well, what we do here is we, as I finish my last example, since it was at 10, I can just go to the home screen and type y, and notice that it gives me my output. In fact, it even shows me a couple extra digits. That 5 is actually that 6 at the end is actually a 5 followed by 2 8s. Now I'm going to store that somewhere. I stored it as b. Because when I do the next thing I'm going to do is when I trace it again or regraph it or do anything else, it's going to change the values of x's and y's. So I store that in a b so I don't have to write that down again. Now we just do a trace again, and this time I type in x is 3 and enter, and here's the point way down here, and it tells me a y there. So when I go back to the home screen, there's y, and what I want to do is b minus y, and there's our value, which is about 37%. So remember what we're doing. So what we're doing is we're finding the two y values, the one at 10 and one at 3, and the difference in those two y values is the probability that we're between. Because remember the b, which was 63%, is the probability that x is less than 10, and then we subtract off from that the 0.259, which is the probability that x is less than 3, and what's left is the probability that x is between 3 and 10, which is what we're after. What if we want to go use the PDF to find the probability? Let's do the same probability just to kind of double check to review. So we got the same graph, but this time we're not going to look at the CDF graph. We're going to go back to look at just the PDF graph. So notice I turned off y2 and turned y1 back on. I had y1 turned off and y2 turned on in the last page. So we just look at that and graph it. This time I may not want to go up as high, so notice I brought the top down, not from 1, but way down quite a bit to 0.11. And I graph that. Once I get a decent looking window, I just do second trace, which is calc. Choose number 7 and tell it the lower limit's 3, enter, upper limit's 10, enter, and it shades it for us and computes that probability. Or I can just do function integrate, type in the formula for this. If I know I have it in y1, I could just type in y1 here instead of typing all this stuff here. Comma x, comma 3, comma 10, and we get the same. So the value that we got here was the same value that we ended up with over here. So two different ways of getting the same thing. Now, sometimes we're interested in going backwards. We're wanting to find what we sometimes call an inverse probability. That is, we know the probability and we want to find the x. See, before we knew the x and we wanted to find, say, the cumulative probability. An inverse probability is you know the cumulative probability and you want to find the x that goes with it. So really, if you think on a CDF, what we had before when we were finding a cumulative probability is we just traced, which basically allowed us to put in an x value, and the calculator, either by the table or the tracing, outputs a y value for us. So we knew the input, we knew the x, and it tells us the output is the cumulative probability. This is for the CDF now, cumulative density function. Now, what we want to do is go backwards from that. We want to know, this time we know the output, we know the y, and we want to turn around and see if we can figure out the appropriate x that goes with that. Well, the way we do that on the calculator is we graph a horizontal line. So notice I've done down here and put y3 is 0.4. So we want to find the x value that produces a cumulative probability of 0.4. Another word for that is the 40th percentile. The x values so that 40% of the time the values are below it. So when I graph those two, I get that middle green there, and I just want to calculate the intersection of the two. And so when I do a calc intersect, I get 5.1 something, and of course a y is 0.4. And so the 40th percentile is approximately 5.1. Now I will say sometimes this is a little bit slow for it to graph this CDF. Sometimes it's a little slow to do the calc intersect. But most of the time it's going to be fast enough that you could get an answer that you need in a reasonable time frame. Now, if you know some calculus, there may be some calculus techniques in some cases that allow us to find an explicit formula for this CDF. Okay, or if we've got the PDF, if the PDF, find the CDF, or the other way around, if we've got the CDF, find the PDF. Okay, if you do know calculus, the PDF is the derivative of the CDF is an antiderivative of the PDF. But in this course, we're not going to assume we know any calculus. We're not going to assume that we know how to find any of these formulas. We're going to do this strictly with calculator techniques to figure this out. Okay? If you know calculus and you know how to find these formulas, or you have them memorized from somewhere where somebody's computed them in general and you want to use that, that's fine. But I want you to know this general technique so you can apply it to a situation, perhaps one you haven't seen before. So let's do exactly that. Let's take a situation, we haven't seen one like this yet. We have a probability density function. P of x is 1/25 times x times e to the power negative x over 5. And this is defined for x is greater than or equal to 0. That is, the probability density function is 0 everywhere else. So we only have to consider positive x's. First of all, this is the PDF. Okay? And first use the TI-84 to graph this and figure out an appropriate window for this. Go ahead and do this now. Press pause. Alright, well now you're back and you've graphed this. Now it may have taken a little trial and error to figure out an appropriate window, but here's what I came up with. Certainly we want to start x at 0 because this formula doesn't apply before that. And I went on out about 35 years. Didn't know for sure how much this would be, but I did a little trial and error until I got that to work out. And also a little trial and error to figure out how tall to make it. I ended up going with a y max of 0.1 and a y min of negative 0.01. Of course, y doesn't go below 0, but I want a little space to show if I want to do any tracing or calculating areas or whatever, that will show up below the x-axis here. So, of course, when you have to do this by putting it in y1, parentheses 1 divided by 25, parentheses times x times e to the power, it'll open parentheses for you, negative x divided by 5, close parentheses. Make sure this is a negative, not a subtract. Turn off y2, but don't delete it because we may need it later. Choose a window, a little trial and error back and forth until we get a good looking window. And there's a nice little graph. You can tell it's skewed to the right there a little bit, but we have a nice little smooth curve. How can we verify that this is a legitimate PDF? We're going to use 200 to approximate infinity throughout the rest of this when we're dealing with this function. There's actually two conditions. What are they? Okay, condition 1 is that the output has to be positive or 0. E to any power is positive. 1/25 is positive, so multiply that's positive. And if x is positive, then the whole thing is positive. So for the x is greater than or equal to 0, this turns out to be a positive or 0 for all your outputs. So that's condition 1 is definitely satisfied. And of course we saw that kind of when we were looking at our graph, that the y's are always above the x-axis. The graph is always above the x-axis. Now, the other thing is the total area. This total area between this curve and the x-axis, all the way out here to infinity, but starting at 0, all this has to be an area of 1. Now, we can't really go out to infinity with the calculator, but we can assume that 200 is going to get us there. Let's see what happens. Okay, well, we just integrate this formula. I type the formula in. Function integrate, math 9. Plug in the formula, comma, x, comma, 0, comma, well, infinity, but we're going to use 200 for that. And sure enough, that turns out to be 1. Now, don't worry about what to use for infinity. On any problem that I'm going to give you in this course, I'll tell you a reasonable thing to use for infinity. But if you try something that doesn't turn out to be 1, go out a little bit further and see if it keeps working out. And go out far enough, it should turn out to be 1. If I go out to 2,000, it should still be approximately 1. So there we are. Alright, now this is a real world type problem. It's a failure of a product is modeled by this. And we want to find the probability that an item will fail within the first 5 years. And then also, second question, what's the probability the product will last more than 5 years? See if you can figure this out now. Figure it out, come back, press pause. Well, if we've got our PDF graphed, the probability that it'll fail in the first 5 years is the shaded part, which is here in the third screen, where I integrated from 0 to 5, 0.264, etc. And of course, 1 minus that is the unshaded region, which is the probability that lasts more than 5 years. The first part of the screen, I actually figured it out directly for the more than 5 years. I did it 2 ways. One is I just did 1 minus, and I found the area under the curve from 0 to 5 and subtracted it from 1. And then I did it directly using 200 as infinity, and did that here when it said from 5 to 200. And if you notice, there's no difference in those. Now technically there is some little bit of area beyond 200, but it's so small it doesn't show up in the decimal places we have here. So it turns out to be what? About 26.4% is the probability that it'll fail within the first 5 years, and about a 73.6% that they'll get at least 5 years out of it before it fails. So what's the average time? Well, not yet. We'll get to that in a minute. What's the probability that it's going to fail somewhere between 3 and 6 years? Go ahead and figure that one out now. Press pause. Okay, now you're back. To find the probability between 3 and 6 years, we can do it from the home screen by doing the same. You can just say second enter and it'll get this back. And this time we're going from 3 to 6 on our integral or our area calculator. And that's about 21.5%. Or we can do it on the graphing screen. We can do, what was it, second trace, which is calc, number 7, left bound of 3, and right bound of 6, and enter, and we get the same number there. And it also shades it for us. Now, what is the mean life expectancy of this product? What is the average lifespan of this project, of this product? See if you can figure that out now. Press pause. Well, remember the mean is the expected value of x. So what I can do is I say x times, and notice I put the entire PDF in parentheses here, and then put x times that, and that's what I'm finding the integral or the sum of. Okay, so I'm summing up x times the PDF from x going from 0 to 200, and that turns out to be 10. So the average life expectancy for this product is 10. On average, they'll last 10 years. That's the mean. How about the variance and standard deviation? Go ahead and compute those now too. Press pause. Okay, well, instead of the variance is the expected value of x minus mu squared. So instead of the x right here, I have x minus mu. I need to figure out mu first, which was 10, the mean. So it's x minus the mean, in parentheses, square, times, then put in parentheses the PDF formula, close parentheses, comma x, comma, 0 to 200 in this case, because that's 200 is our infinity here. And so that turns out to be 50. So the variance is 50. The standard deviation is the square root of 50, or approximately 7.07. Now let's use the calculator to draw the CDF. So go ahead and do that now. Please press pause. Here we are. So this time I turn off y1, turn back on y2. Now in this case, the probability that x is less than or equal to 0 is 0, so I'll leave this as a 0 right here. And then continue on. In this case, I decided to go out about 40 years, and we're pretty close to having a probability of 1 after we've gone out 40 years. It's not quite, but almost. And so we get a pretty good idea of seeing the graph level off at that point. Of course, start at 0, and we're eventually going to end up at 1, so I basically want to go from 0 to 1, and I'm just going to go a tenth beyond that. So when you're doing the CDFs, I almost always go from negative 0.1 to 1.1, and that usually works out pretty well. That's for the y's, of course. And then hit enter, and it takes us a little while to figure it out, because it's doing a lot of numerical calculations in the background to approximate this thing. But it comes up here and gives us a nice looking graph. I have it grown a little thicker than normal. Now, can we use the CDF to compute the probability the item will fail within the first 3 years? You can also do it from the PDF, but let's do it from the CDF this time. Go ahead and do that on your own now. Press pause. Well, we're back, and all this is just the output of the CDF. So we just type in trace, type in 3, and enter. Or we could have looked at our table and saw 3 in the table, and either way we would get a y value of 0.12190,138, or about 12.2%. So probably the item will fail within the first 3 years is about 12.2%. What's the median of this distribution? And interpret your answer in the context. Well, what is a median anyway? A median is an x value where half of the probability is below it. So what we don't know is the x value. What we do know is the cumulative probability. So basically this is a class of problems where we know the cumulative probability and we want to find the probability. Turns out that's nice if we have our hands on the CDF, either a formula or especially if we can get a graph of it, whether we actually know the explicit formula or not. We can use that graph to help us find that value. See if you can do that now. Press pause. Well, this is an inverse probability. An inverse probability is where you know the probability, cumulative probability, and we want to find out the x. So what we do is we type in the cumulative probability as y3. That gives us a horizontal line here at 0.5. And we want to find this point of intersection by doing calc intersect. And of course we know y is 0.5. That's the cumulative area, because y values on the CDF are probabilities, are cumulative areas under the PDF, or total probabilities up to that point, cumulative probabilities. And of course what we want to know is the x value, which is about 8.391735. Okay, and that's a typo. That should say 8 not 5.39, but 8.39. So I've got it right over here. So that median is about 8.4 years. So 50% of the items will fail within about this 8.4 years. Well, here's another inverse probability for you. Find the amount of time it takes until we have about 75% of the products released will fail. So if they release them today, how long will we wait till 75% of them don't work anymore? Press pause now and figure that out. Well, just change the 0.5 to 0.75. That raises your horizontal line up. Do a calc intersect, and that turns out to be about 13.46 years after purchase when we get 75% of the products will fail. Let's take a quick look at this on the calculator, where you can actually see the calculator working here. So here we have this particular example that we just looked at, typed in as y1. So you hit your y equals key and type that in. I think this graphing window is set up for for the CDF. Yes, it is. So let's go ahead and graph it, set it for the PDF. We can still do 0 to 40, but we don't need to go nearly as high. I forgot now what we needed for that. Let's say we go up to 0.4. Let's see what that looks like. We may have to do a little adjusting. Okay, that's not high enough. So this is 0.4, 0.3, 0.2. 0.1 is probably going to be high enough. Okay, see how you have to do a little trial and error here? Okay, and so we go up to the top y, 0.1, and let's take about 1/10 of that for how far we want to go below the x-axis for the minimum y. Alright, now let's take a look at that graph. Oh yeah, that's a pretty good looking graph for the PDF there. So now we have a nice little look at the graph. Now if I want to find probabilities on here, let's say the probability that x is between 1 and 4. How about 5 and 10? Let's say x is between 5 and 10. We can do it from this screen by doing second calc, and we want to do number 7 there, so just press 7. And we said we wanted between 5 and 10, so we click 5 and enter, and 10 and enter, and it shades it and tells us that's about 32.975%, about 33%. If we quit this and we go to the home screen, then we can do it directly here by going Math 9. Now if I know it's in y1, I can just type y1 here, but I can also type in the formula, which is 1 over 25. I'll put that in parentheses, let's see, times x times e to the power negative x over 5, close parentheses, with respect to x. And I wanted to go from 5 to 10 in this case, so 5, 10, and that gives me my same number that I just got out of the calculator a while ago. Now if I go back to the graph, it's going to show that shading. If I try to shade something else, that shading may get in the way. So let's clear that off by going second, program, which is draw there. And the first one's clear draw, so I'm just going to hit that enter a couple of times. Actually just once will do it. And that clears my drawing off. Okay. And we can do all kinds of probabilities based on this particular one. Now we want to graph the CDF, for example. I turn this one off by putting my cursor on the equals, hit enter. Now if I delete this, the CDF's not going to work right. But I put my cursor on that, hit enter. This will graph the CDF. The CDF I can use the same x's I used for the PDF, but I'm going to always go from negative 0.1 to 1.1 is a really good window for the y's. So let's graph that. Let's see, if I'm going to go to 0 to 40, maybe I want to mark off only every 5 for the x's there. Now this is a little bit slow. You'll get to see right here how long it takes. Okay, but this is graphing the cumulative probability. Okay, so this cumulative probability is here, and we can use this to calculate both cumulative probabilities and inverse cumulative probabilities. In other words, if I know the x, I can figure the cumulative probability that x is less than or equal to that x value by just doing a trace, entering the x, and it'll tell me the y. Or if I want an inverse probability, I can graph a horizontal line at the probability we're trying to reach, and it will give me the x. So for example, if I hit trace and I plug in 7, enter, it'll go to the point x is 7. It'll tell me the probability that x is less than or equal to 7 is about 0.408. If I want to go the other direction, I can come over here, and I've already got one set up. Maybe we'll do a different one. Let's say I want to go 25%. Find the 25th percentile. Find Q1 here. Okay, now I can graph that, and that's going to graph a horizontal line there. And I just want to calculate where these intersect. Calc, intersection here, enter, enter, and I can enter a number or a value. It works a lot better if you get pretty close. Okay, that's pretty close to where they cross. Hit enter, and it will compute. Of course, the y is going to be 0.25. It'll compute an x for us. Looks like it's somewhere in the vicinity of 4. 4.8. Okay, so that says the 4.8 is the Q1, the lower quartile, the 25th percentile, 25% of the time. This will happen below 4.8. So that gives you some idea of how to use your calculator for these types of problems.